In the next example, we have the integral of cosecant squared of 8x with respect to x. So because it's not just cosecant squared x, which is a basic antiderivative rule, it's cosecant squared of something else, we will use a substitution. So here I'll choose that u is equal to 8x, since 8x is inside of the function cosecant squared, and the derivative of 8x is just 8, which we will end up dividing by for dx. So 8x we will replace with u, and dx we will replace with du over 8. So the 1 over 8 will be a constant in the front, and we have the integral of cosecant squared u du, which is a basic integral in u. So the antiderivative for cosecant squared u will be minus cotangent u plus c, and we can rewrite it back in x. The antiderivative is minus 1 over 8 cotangent of 8x plus c. Again, it's up to you. If you want to check your answer, you can take the derivative of the antiderivative and see if you get back the integrand. So the minus 1 over 8 will keep as a constant in the front, and then we have the derivative of cotangent u, which will be minus cosecant squared u times u prime. So the derivative of the antiderivative is cosecant squared of 8x, which gives you back the integrand, so it's correct. Next we have the antiderivative of 1 over 3x plus 25 squared with respect to x. So here again we don't have a basic integral, so we'll try the substitution. U is equal to 3x plus 25. Since 3x plus 25 is squared, and also the derivative of it is 3, which is a constant that we can adjust. So we will replace 3x plus 25 with u and dx with du over 3. So the 1/3 will keep in the front, and we'll have the integral of u to the minus 2 du. U to the minus 2 is a basic integral in u. The antiderivative will be negative u to the power minus 1 plus c, and then we can put the antiderivative back in x. So the antiderivative is negative 1 divided by 3 times 3x plus 25 plus c. In the next example, we have the integral of ln x to the 5 over x with respect to x. Again, this is not a basic integral in x, so we can try a substitution. Here we could choose ln x to be u, since it's in this power 5. Also, the derivative of ln x is 1 over x, which appears in the integral. So u will be ln x, and du is the derivative of ln x, 1 over x, times dx. So here we'll replace dx over x with du, and instead of ln x to power 5, we'll have u to power 5. So now we have the integral of u to the 5, which is a basic integral in u. So the antiderivative for u to the 5 is u to the 6 over 6 plus c, and we can replace it back in x. It will be ln x to power 6 over 6 plus c. Next we have the integral of x squared times e to the minus 5x cubed with respect to x. Again, this is not a basic integral in x, so we can try a substitution. If we choose u to be minus 5x cubed, the derivative of minus 5x cubed will be minus 15x squared, and besides the minus 15, x squared appears in the integral. So we will replace minus 5x cubed with u, and x squared dx with du over minus 15. So the minus 1 over 15 we can keep in the front, and we'll have the integral e to the u du, which is basic in u. So the antiderivative for e to the u is e to the u, and when we replace it back in x, the antiderivative is minus 1 over 15, e to the minus 5x cubed plus c. Next we have the integral of e to the 7x over e to the 7x plus 7 with respect to x. So I will choose e to the 7x plus 7 as u, since it's in the denominator, and also the derivative of e to the 7x will be 7 e to the 7x. So besides the constant 7, e to the 7x appears in the integral. So then I can replace e to the 7x plus 7 with u, and e to the 7x dx with du over 7. So we have 1 over 7 in the front, integral du over u. Just recall that 1 over u, or u to the minus 1, has its own antiderivative rule. The antiderivative is ln of u in absolute value. So if we put it back in x, the antiderivative is 1 over 7 ln of the absolute value of e to the 7x plus 7 plus c. And since e to the 7x plus 7 is always positive, we let go of the absolute value in the final answer. The following problem is about the population of wolves in a habitat. The growth rate of a population of wolves n is given by dn by dt is equal to k times 750 minus n. T is in years and k is a constant, where 750 is the limiting capacity of the habitat for that wolf population. When t is equal to 0, the population is 100. After 2 years, the population grows to 160. And the question is to find the population function n of t. To solve this separable differential equation for n, we'll separate the variables to either side of the equal sign, and then integrate both sides. So here we divided by 750 minus n on the left, and k dt on the right. Next we'll integrate both sides. The integral on the right is a basic integral since k is just a constant, and for the integral on the left we'll use u substitution. So here we'll set u to be 750 minus n, then du will be negative dn. So we will replace dn with minus du, and 750 minus n we'll replace with u. So now the integral on the left is basic in u, so we can integrate. So the integral on the left is ln of u in absolute value, and the integral on the right is kt plus c. Next we'll replace back u is 750 minus n, and since from the problem we know that 750 is the limiting capacity, n will be less than 750, so the inside of the absolute value is always positive. So here we let go of the absolute value. We have ln of 750 minus n is equal to, and the negative we transfer to the right side, negative kt minus c. We can solve this logarithmic equation for n by exponentiating both sides to base e. So on the left we just have 750 minus n, and on the right we have e to the minus kt minus c. Using the exponent laws, e to the minus kt minus c can also be written as e to the minus kt times e to the minus c. So here we'll rewrite e to the minus c as constant a. 750 we'll bring to the right side by subtracting, and we'll multiply by a negative to isolate n of t. So the population function is 750 minus a e to the minus kt. We can determine the values of the constants a and k by using the initial conditions that were given in the problem. So the first condition is that at t is equal to 0, n is 100. So if we plug it into the formula, we get that 100 is equal to 750 minus a times e to the 0, and e to the 0 is 1. So a is 650. So n of t is equal to 750 minus 650 e to the minus kt. The second condition, n is equal to 160. So 160 is equal to 750 minus 650 e to the minus 2k. So here we have an exponential equation. We can solve for k by isolating the exponential and then taking the natural logarithm of both sides. So 160 minus 750 is minus 590. Next we'll divide by minus 650. The negative and negative will cancel, and we can also cancel the common factor 10 in the top and bottom. So e to the minus 2k is equal to 59 over 65. Next we take logarithms of both sides. So on the left we have ln of 59 over 65, and on the right we just have minus 2k. So k is equal to minus 1/2 ln of 59 over 65. Using the log law, we can write the coefficient minus 1/2 as the power, and since the power is minus 1/2, we can take the reciprocal and square root it. So k is equal to ln of the square root of 65 over 59, or around 0.0484. So the wolf population is given by this function. Population modeling can help to predict and manage the future of a species and its habitat.